Hey, good morning, everyone. Welcome to the Young Imagineers Challenge 2020 live lesson, beaming to you live. I want to say the Science Museum because I host this every single year. We've been doing the Young Imagineers competition. I host it from the Science Museum, so I always look forward to that moment where I can say, "Welcome to the Science Museum." But sadly, not this year. Welcome to my sitting room, which is I've tried to make look a little bit like the Science Museum for you. It's such a pleasure to be here doing this live lesson for you. And I just want to say very quickly, a huge thank you to the Science Museum and to Equinor and to the producers of Young Imagineer for making this happen this year. But most of all, I want to say a massive thank you to you guys for all of your entrants, all of your brilliant ideas. We asked you, how can we make the world a better place? What would you like to see? What challenges would you like to see met? And we had over, gosh, 300 or so entrants, and I read them all, and absolutely fantastic ideas. And the thing that struck me the most actually was that most of your ideas are actually ideas that people, real scientists, real engineers, are actually thinking about as we confront all kinds of problems with things like sustainability, with things like the environment, with things like health. And technology and your creativity are exactly what we need to improve life on Earth as we know it. So first of all, a massive thank you to you. I want to say as well, well, I should first of all, I should introduce myself. For those of you who don't know me, my name is Dallas Campbell, and it's my honor to be one of the hosts of the Young Imagineers every year. And when I'm not doing that, I present and produce various science and technology programs on television. So I have the great privilege of doing that. And what I get to do for a living is to really explore what science and technology is all about. And I get to tell the stories of scientists and what's going on and how the world works. It's a bit like having a backstage pass to understanding how the world works. And I love science. For me, really, science is it's kind of a big adventure. It's a little bit like if you kind of go out walking on the beach and you're turning over stones to see what's underneath. It's that sense of excitement and curiosity that really makes science fascinating. And I'm sure you like me, sort of share that love of science. So today's lesson is called Technology Making Waves. And what do we mean by making waves? Well, it kind of has a bit of a double meaning. So making waves can, it can be about changing the status quo. If you make waves, you're shaking things around and making things different. And I've been thinking about the kinds of technologies that we have now, and also the kinds of technologies that we had when I was your age, when I was at school. So just things like all the things that we take for granted on a smartphone, things that you can do on a smartphone, like make a telephone call. I've got a few things that this is what technology used to look like. So telephones, they used to look like this, and they had cables, and you used to be able to, hello? Oh, no, wrong number. But there you go. Oh, it's not plugged in. So there you go. That's what a telephone used to look like. Things like music, things like when we wanted to listen to music when I was a kid, we didn't have Spotify and apps like that. We used to have things like this, records. So this is a sort of vinyl record. This was the kind of height of technology when I was a kid. And what is it? Well, basically, it's just a piece of plastic disc with a groove on, and you put the needle on there. I've got my record player over there. I still listen to records, and that's how we'd listen to music. Things like film as well. Of course, now we're so used to looking at film on our smartphones, but if I wanted to watch a film when I was a kid, you'd have to go to the cinema, and they would project great reams of this stuff. This is an old film. In fact, this is the very first telly thing I ever did, which I still have on film. Sadly, of course, I don't have the technology to play this anymore. But anyway, the point is that technology is constantly changing. It's constantly evolving. It doesn't stay still at all. There's a special bonus prize, actually, for anyone for the old teachers here who knows what this album is. Some of you will know. I might actually talk about this in a little bit as well. Before we crack on, I want to say, if you've got any questions, ask them using Facebook or however you're meant to be asking questions, and they'll somehow, by the powers of magic, will get through to me, and then I'll hopefully be able to answer them, maybe at the end if we've got time. I'm going to try and be very strict for time because I know you've got other things to do. So anyway, so technology, it's constantly changing, it's constantly evolving, it constantly responds to the challenges of the world. So we've had lots of challenges this year, and of course lots of your ideas about challenges have reflected that. And technology is such a brilliant tool. And right now, we're in the middle of what I call a sort of technological revolution. We've had technology revolutions before, things like the invention of the printing press, where suddenly everybody could read and have access to information. But the digital world is absolutely fascinating. The digital world, the internet, smartphones like this, computers, information technology, AI, all these different things are revolutionizing the way that we live on planet Earth, the way that we communicate, the way that we do things. And it's really, really exciting, especially for you guys who are coming up, who'll be able to make it even better. But technology is the point about technology. If you think about that word, it is the stuff that we make, the things that we make. But underneath technology, it relies on solid science. So technology is nothing without the science. And actually, that was the first thing I wanted to talk about, because making waves kind of refers to another kind of wave. The waves that the physicists amongst you will be able to recognize, what we call the electromagnetic spectrum. So all around us, we are bathed in this sea of energy, invisible energy in the form of waves. Now, some of the waves we can see. So for example, visible light, the fact that you can see me, the fact that you can look around and see colors, that all comes down to visible light, which is part of the electromagnetic spectrum. In fact, going back to my record very quickly, very, very famous scientist, Sir Isaac Newton, of course, was sitting at home in his Woolsthorpe Manor in Lincolnshire. He had the curtains drawn on his windows, but there was a hole in the curtains and a beam of light, visible light, came through the curtains, hit a glass prism that was just on his desk. And he noticed that that white light refracted into all the different colors of the visible spectrum, the rainbow that you're all familiar with. And that is the electromagnetic spectrum. Each one of those colors represents a wavelength of visible light. Now, but it's not just visible light. I've got a little slide I want to show you. Egla, if we can have the slide of the electromagnetic spectrum, you can see that there's all different kinds of waves of different wavelengths. So right on the left-hand side, you've got these huge waves, radio waves, which are about the size of buildings. Now, of course, we use radio waves, listen to the radio and television signals and communication. Getting smaller, so waves that are about the size of humans, microwaves, where you're familiar with cooking, but also communication. We use microwaves to communicate. Then infrared waves as they get smaller. And then we get into the visible part of the electromagnetic spectrum, the bit that we have evolved, our eyes have evolved to see. Beyond that, as the wavelengths get smaller, ultraviolet, then we get into X-rays, of course, you know what X-rays are for. Tiny, tiny waves, the size of atoms. We use X-rays, really, really useful, of course, for seeing inside the body if you've got a broken bone. And then things like gamma rays, that absolutely tiny, the size of nucleuses. So that is really the electromagnetic spectrum. I want to start off, actually, before we go into the sort of technology, I want a big congratulations first to Taryn from Solihull School. And I wanted to point out your particular bit of technology first, which was all about battery packs and how battery packs can be universal for charging cars. And it was a really, really good idea. And in fact, it got so many votes. There's going to be some prizes winging its way from the Science Museum to you. So that's our Taryn, you're our inspiration really for today's lesson, all about waves. My friends at the Science Museum, they've got a little film about the electromagnetic spectrum, and then we're going to talk a little bit about the technology that we use that relates to the electromagnetic spectrum. But we're going to show you a little video, and after we've seen the video, there's going to be a little quiz. I want you to watch this video very, very closely. And then afterwards, I'll ask you a few questions. So, Egla, let's have the video.
Why do we need to know about the electromagnetic spectrum?
Because electromagnetic waves are incredibly useful. Radio waves are used for sending radio signals. That's how you can listen to your favourite FM radio station. And you're also using radio waves to control your radio-controlled car. And as for microwaves,
Everyone knows they're used for cooking in microwave ovens.
but did you know that microwaves are also used for sending satellite signals?
Satellites use microwaves?
Yes, they use a frequency of microwave which easily penetrates the Earth's atmosphere.
And as for infrared, very useful. TV remote controls use infrared signals to change TV channels.
Meanwhile, the North...
And police use infrared night vision cameras in their helicopters.
Visible light. We see things using visible light waves.
True, but they're also used for sending information down an optical fibre.
Optical fibres. Like in my optical fibre lamp.
Exactly the same principle.
And ultraviolet. They use ultraviolet lights in nightclubs.
Yes, and if you're wearing something white, then you'll very easily be spotted.
And can't you spot a dodgy banknote by putting it under an ultraviolet light?
Yes, banknotes have a hidden security mark, which is only visible under UV lighting.
And X-rays are used for detecting broken bones.
And they're also used for detecting broken pipes buried underground.
And what about gamma rays?
Gamma rays are used for killing cancer cells, but they're also used for sterilising things, because they can kill all the bacteria on a plastic syringe without melting it.
So electromagnetic waves are really useful.
Wow, so there you go, electromagnetic waves, the sort of fundamental physics of the universe. We are bathed in all these rays, and we can construct technology and actually utilize them. Okay, were you paying attention to that film? We're going to do a little quiz, and the way you can do it, it's thumbs up if you agree, or thumbs down, and your teacher will be the adjudicator, and I'm sure will offer you fantastic prizes to whoever wins. Okay, so question 1, based on that little film. Radio waves help us listen to the radio. True or false? So thumbs up if you think that's true, thumbs up if you think that's false. Radio waves help us listen to the radio. It is true. Yes, well done if you got that right. Question 2, microwaves help us send signals from space using a satellite. True or false? It is, exactly, it is true. Question 3, infrared helps us heat up food. Thumbs up, thumbs down. I can't see you, so I'm just having to trust you. Infrared helps us heat up food. It's false. No, infrared, much more useful for things like TV remotes. We can see, this is question 4, we can see visible light. True or false? It's true. Yes, of course we can. Question 5, UV light is used to check whether pound coins are fake. It's false, of course, not pound coins, but banknotes. They have that special security feature that utilizes ultraviolet light, which lets you be able to see if they're fake or not, because it's very hard to forge them. This is an easy one. Question 6, X-rays help us see broken bones. True or false? True or false? True or false? It is true. Of course it is. And lastly, gamma rays help us kill cancer cells. Gamma rays help us kill cancer cells. Is that true or false? It is true, absolutely true. So well done. I can't see you, so there you go. But that's a little bit of a look into the wonderful world of the electromagnetic spectrum. But now we know a little bit about some of the waves that we've been talking about. Here's another bit of technology that a lot of you focused on when you were doing your challenge ideas, and it was this. It's the smartphone. So many of your ideas were reliant on apps and smartphone technology. And also using smartphone technology to really, really make positive changes in the world. I just want to highlight a couple. We've got Daisy, Daisy at Croydon High, who wanted to use smartphones for making road safety, so an app for road safety, which is a really, really good idea. And also Sunny from Grasby, I hope I pronounced that right, Grasby All Saints CV Primary School, thinks that mobile phones should be used to send kind messages rather than mean messages. This is something we're going to look at in a moment, the way that we communicate. But I thought that was a really, really good idea. Some way of filtering out nasty messages. I thought that's a really, really good idea. Now, of course, mobile phone technology, the thing that makes it so brilliant is the fact that it's completely wireless. It's not like my old telephone here. It relies on radio and microwaves to be able to communicate with satellites and other things. And that's what makes it absolutely brilliant. We're going to learn a little bit about satellite technology and space in a moment. But there's a different revolution as well going on with mobile phones that I'm particularly fascinated, not just the fact that it utilizes the electromagnetic spectrum, but it's what mobile phones are made of. We're in the middle of a materials revolution. So a lot of the old technology that I showed you earlier on is actually pretty simple. It's made of one material. It's made of plastic, or it's made of acetate, or it's made of, you know, a telephone, obviously it's made of things like bakelite, a type of plastic. It's got a copper wire here and metal. But orders of magnitude more complex as things like a smartphone. Now, I've got a little slide, Eglo, if you can bring this up. This just shows you some of the elements, some of the materials that go into a smartphone. And it's a lot of materials that we see in what we call the periodic table of the elements. So on the screen itself, things like aluminium and silicon and the electronics have all kinds of different materials, things like neodymium and batteries and rare earth metals, all this kind of stuff. But to really, if you're a material scientist, to really understand materials, you have to not just understand the phones themselves, but the entire infrastructure of mobile technology that is in place with us now. It's absolutely spellbinding. But to really understand materials, you have to understand things like how they behave in temperature. So for example, if you're building a satellite that's going to be making your smartphone work, you have to understand how things work in really extreme temperatures. And also you have to understand the fundamentals of material science as well. So we can go right back to the beginning. I'm going to go back to my friends at the Science Museum, who are going to talk to us a little bit about materials and temperature, just to give you an idea about what I mean.
Thanks, Dallas. You're right. Temperature can make a huge difference. We are here in Wonderlab, the Equinor Gallery, to play with some pretty extreme changes of temperature.
My name's Sam, and today we're looking at the states of matter and the changes between them. And we're going to be using one of the coolest things we have here at the Science Museum. Not me, it's liquid nitrogen. Now, liquid nitrogen is minus 196 degrees Celsius, which is an extreme change of temperature from the room temperature around us here. And we're going to use that extreme change of temperature to do some pretty fun things. So Alexandra has a rocket balloon filled with gas that she's breathed into it. The container is filled with liquid nitrogen. So let's see how Alexandra's gaseous breath that is filling up all the space in the balloon reacts to meeting the minus 196 degrees C nitrogen. As you can see, the balloon shrinks. And this is because when the gas in the balloon gets cold, it condenses, it turns into a liquid. And liquid takes up about 1,000 times less space than the gas. Alexandra's now going to take the balloon out of the nitrogen, and you should hopefully be able to hear her breath sloshing around in the balloon as a liquid. Very quickly, the heat from the air, room temperature about 22 degrees Celsius, goes into the cold liquid breath in the balloon and turns it back into a gas. And the balloon swells up again. And now we're going to be doing a demonstration where we can see all of the basic states of matter and the changes between them. So Alexandra has a bottle in which we're pouring liquid nitrogen. And as the liquid nitrogen is so much cooler than the air around it, it's already boiling. You can see it bubbling throughout and turning into a gas. We're going to trap this gas in a balloon, and you can see it's already starting to inflate. We are then going to make this process speed up by putting the bottle into water, which is a better conductor of heat. The nitrogen turning into a gas takes up 1,000 times the space it did originally. This is going to keep inflating until the balloon explodes. And you'll see all that cold nitrogen in the air condensing this water around it and looking a bit like a cloud. If Alexandra takes the bottle out of the water, you can see it's encased in ice. This is because the heat has moved out of the water into the cold liquid nitrogen contained within the bottle, causing the water to freeze. And if we stayed watching that ice long enough, it would melt. So that's all the basic states of matter and the changes between them using some awesome liquid nitrogen.
Thank you very much, Alexandra. Basically, Alexandra has the best job in the world, which is to blow things up at the Science Museum. It's brilliant. So there we go. The science behind technology is really important. We've looked at the electromagnetic spectrum. We've looked a little bit about materials. I've just noticed, actually, of course, my glasses case also handily has the periodic table of the elements on it, in case I forget. But understanding how matter behaves, understanding how materials behave, understanding how they behave in things like cold temperature, really, really important and really, really fascinating. So thank you for that. Now, many of your entrants or many of your ideas were centered around the internet and particularly about the way in which we communicate with each other. How can we make social media a safer place, a nicer place to visit? How can we make the internet more friendly? I want to say thank you to Ruby at Nutton St. Mary's Primary Academy. I hope I've got that right. And also Thomas from the Lighthouse School. Both of you had this idea of highlighting the fact that the way that we talk to each other, particularly online, has real world consequences. So things like online bullying and this kind of stuff is really, really important. So I want to say thank you to you two, particularly for pointing that out. It is indeed a really, really big challenge. And in fact, it kind of reminds me of another sort of story of technology, the technology of how we communicate. Now, if we go back to when I was a lot younger, of course, we didn't have the internet. So if we wanted to communicate, we had to do things like write letters. And in fact, I kid you not, I had my first postcard that I've had for years today, actually. It came in the post today. So I got a postcard. So this is how we used to communicate. We used to write postcards, and it's from my friend Will. So thank you, Will, for my postcard. Dear Dallas, I hope you're okay. I hope the guitar is making sweet, mournful music. Anyway, I like to play the guitar. Anyway, my friend Will knows that. So he took the trouble to actually sit down and write a letter. And of course, I guess not many people spend the time writing postcards. Occasionally, some of you might write Christmas cards as we go into Christmas. But of course, writing things down, paper and pen, was the earliest form of communication technology. And then, of course, we had electricity came along and we could do things like Morse code. So you'd have copper wires and you'd be able to go beep, 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 and you'd send coded messages across wires and you'd be able to descramble them. And then, of course, things like the telephone, hello, still no one there. No one there. Came along and we could talk to each other. But now, of course, we've got mobile phones. In fact, these would have been completely unheard of when I was at school. The idea of having a phone that wasn't connected to wires would have been bizarre. However, I want to tell you something about wires. We tend to think of wires as being sort of rather outdated, but in fact, the internet itself is dependent on cables, and you wouldn't really think of it. Now, we saw a little picture in the first film about the electromagnetic spectrum. Do you remember he had a sort of what we call a fiber optic cable? It was like an ornament, and you could see the little lights at the top. And they said that actually fiber optics can carry data, and he's absolutely right. This is this is a picture of a cable, a giant cable that runs underneath the Atlantic, and it's a fiber optic cable, and you can see those little fronds that are coming out at the end. Actually, what they are, they're not carrying copper wires or electricity, they're actually carrying visible light. So you can actually send visible light down a cable and it will carry data at the speed of light. And we tend to think of, you know, cables as being sort of quite old-fashioned, but I've got a map that actually shows you just how many cables there are underneath the ocean that are connecting us all up. So if we can see that map, there you go. Absolutely loads of cables. So you can see cables going from the United States to Britain, to Europe, and then going down to South America, even up there to Iceland and Greenland. So cables are still really useful. I'm going to talk a little bit about satellites in a moment. But if you think of fiber optic cables as being quite a sort of modern invention connected with the internet, I want to sort of take you back in time. I've got a little film from the Science Museum that's going to show you the very first time we actually built an undersea cable. And it's a really, really nice film. So if we can have a look at this little video.
Yes, can you believe it? There are huge networks of underground cables that travel thousands of kilometers long. Let's find out about the first transatlantic cable.
Slap bang in the middle of the Atlantic Ocean, the biggest ship of its era. The men on board have no ordinary mission. They're trying to change the shape of the world. In the 1850s, the Victorians are wrestling with a problem. Their world is just too big. They have managed to shrink some of it with networks of telegraph cables that carry messages instantly across cities, countries, even continents, but not across most of the world's surface. Because when information hits the oceans, it screeches to a halt. Good news and bad, profit and loss, declarations of love and war, all have to travel by ship. Send a quick note to America? You'll be waiting 4 weeks for the reply. So, why not wire up the ocean? Well, they try, and fail, spectacularly. The cable's too thin, the ships are too small, the job's just too big. And this isn't the only project to go spectacularly wrong. Engineering megastar Isambard Kingdom Brunel has had another one of his big ideas. To build a Victorian supertanker, 6 times bigger than any other ship afloat. She's called the Great Eastern, and she's cursed from the off. The construction company goes bust, the launch fails, and then Brunel dies, leaving his friend Daniel Gooch holding the baby. He vows to turn her fortunes around. With this, engineers have designed a new telegraph cable to work undersea. They make 2,300 miles of it, enough to reach America, but so heavy that no ship on Earth can carry it, except the Great Eastern. They attach one end of the cable to Britain, and together with 120 sheep, 20 pigs, and 12 oxen to feed the 500 men on board, they set off on their mission to shrink the Atlantic. Day in, day out, night after night, through storm and fog, they lay the cable into the ocean. While in mission control, they watch anxiously to see if the cable's still getting a signal from the motherland. And they almost make it. But just a few days off the American coast, the signal flatlines. Disaster. The cable snapped. It's over. But Gooch is not the quitting kind. He and his business partners stake their own fortunes on one final gamble. A year later, the Great Eastern heads west again. And on Friday, July the 27th, 1866, the dream is still alive when the coast of America is sighted and the connection is finally made. 2 continents touch, clasp hands, no longer so far apart. Gooch and the Great Eastern didn't stop there. They took on the world, putting new lines on the map, new ways for nation to speak unto nation, making the Earth a smaller place and the information age a reality.
So there you go. That is the birth of the information age. So if you think about cables as being old-fashioned, well, some cables are kind of old-fashioned, but we still use them. We still use them. For our last few minutes, I want to talk about another revolution in technology, and that is about how we utilize space. Nowadays, we have loads and loads of satellites flying around the Earth, which tell us, not just looking out into space to tell us about the cosmos itself, although we have those, but actually satellites looking back down at the Earth, so to better understand the Earth and also to better communicate. So mobile smartphones use satellite technology too. But again, a little bit like those cables, that has happened quite slowly. We've had satellites for just over 70 years or so. I want to show you a picture of the very, very first satellites. And this is called Sputnik 1. And this was launched in 1957 by the Soviet Union. It was the first time anyone had launched anything into space. And on board that satellite was nothing more than a radio transmitter. So it sent out a little radio pulse, beep, 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 as it went orbited around the Earth, and nothing more than that. But it marked the beginning of an incredible technological revolution. And nowadays, that revolution has become even more profound. As satellites get smaller and more complicated, we can do more and more stuff with them. We can understand things like the climate. We can understand things like how people behave on Earth. We can understand all kinds of things about the planet simply by satellites looking out and looking in. I've got another picture of a satellite here. This is what we call the Starlink satellite. This is Elon Musk and SpaceX's Starlink satellite array. These are tiny, tiny satellites. And they get launched sort of 60, 70 at a time in a big train. And what they're doing, they're helping remote parts of the world get broadband internet access where normally they wouldn't be able to. You wouldn't be able to put cables. So satellite technology and radio waves and microwaves are able to now cover the Earth. So we can get broadband technology sort of wherever you want. I've just realized I've got a question that's come in from. I'll answer questions in a bit. If you do have questions in our last few minutes, put them in the question box, and we'll go through some of those if we've got time. So yes, satellite technology really, really important. But the problem we've got, and this is where this extraordinary revolution in launch technology is so important is how do we get satellites into space? Because we have a problem. We live on planet Earth at the bottom of a gravity well. There's lots of gravity. So in order to get a satellite into space, you have to send it really, really fast on a rocket. And rockets are expensive, but new technology and new ideas are making that cheaper and making it more accessible. And I'm going to hand over our final video. I think our friends at the Science Museum have got a little rocket demo they're going to do for us. Can we have a look at that?
Not lying about how hard it is to get out into space. To get out into space and out of the Earth's atmosphere, you need a rocket, which needs to work really hard against the force called gravity.
So now let's take a look at Newton's third law. Newton's third law states that for every action, there is an equal and opposite reaction. But what does that mean? Well, every time something is pushed in one direction, there is an equal force pushing back in the opposite direction at the exact same time. Now, to help us understand that a little bit more, we're going to be launching our very own rocket. I have my rocket here, and I've got a gas called hydrogen. Now, in a second, I'm going to fill my tube with hydrogen. Now, hydrogen is really, really flammable. That means it burns really easily. So when it mixes with the oxygen in the tube and I light it, we should get a big explosion. Let's take a look. Wow! So we saw our rocket fly high up into the sky. Now, what was actually happening? Well, we created a huge explosion at the bottom of our rocket. So that caused a downward push. Now, we know from Newton's third law that every time there's a downward push, there has to be an upward push happening at the same time. And it was this upward force that pushed our rocket high up into the sky.
Thanks, Dallas. That's all from us here today, but the Science Museum looks forward to sharing more with you very soon.
I hope so too. One of the things about this year, this terrible year we've had, is that I haven't been able to go to the Science Museum very much. And I love the Science Museum. Hey, who knew? Isaac Newton, I tell you what, our greatest scientist, so he knew all about optics and the electromagnetic spectrum. He knew all about gravity too. Listen, I tell you something, as we come to the end, any questions, stick them in the question box. It's been such a pleasure doing this lesson. And I just want to encourage you to keep thinking about science and technology. How can you make the world a better place? What ideas can you have now that we might be able to see in the future? What technologies can you improve? Or can you think of a technology that hasn't been thought of that will make the world a better place? And it's worth thinking about these things. It's worth reading about the history of science. It's worth experimenting at home with all kinds of things. In fact, thinking about rockets, actually, I love rockets, and you can see I've got my spacesuit here. If you don't have any hydrogen and a Pringles can at home, I've found there's a really good way that you can make a rocket that you can demonstrate Newton's third law, which is, and we'll end on this, I think. One of these, old people like me will know what these are. This is a little plastic pot that we used to keep film in, not film like the movie film, but for photographs. But they make really, really good rockets. And I filled it with a very, very powerful rocket fuel called water, about half full. And if you put something fizzy in it, I've got like an Alka-Seltzer tablet or anything fizzy, like a vitamin C tablet, something like that. What'll happen is it'll fizz, it'll give off carbon dioxide. And if you can trap that carbon dioxide, what'll happen is that the pressure will build up and eventually something will break, and it should send the rocket, if I do this right, up to the ceiling. So that's fizzing away. I'm going to put the lid on nice and tight, give it a shake, and stand well back. And if we do a countdown from 10, 9, 8, 7, 6. There you go. So there you go. You can make your own rocket, demonstrating the scientific principles behind things like rocket science. So there you go. It's been a huge pleasure for me. I'm going to just go through any questions. Oh, here we go. We've got one question from Moorstone, Moorstone Hampstead Primary School. Does the wave come from the glass part on the end of the remote control? Well, yes, it does. So that little glass, I might have a remote control here, actually. Let me see if I've got a remote control. Yeah, here's a remote control. So here is a remote control here. And you can see that little glass part there that actually focuses the infrared. So it doesn't just spray out everywhere. So it doesn't actually come, it actually comes from inside here, but that little glass bit helps focus it. So thank you very much for your question. Although we don't really use remote controls that much anymore. So in a way, this is kind of quite an old-fashioned technology. Anyway, I'm going to go. We've got a couple more lessons coming up for you next year. But it's been a real pleasure. Thank you so much for all your entrants, for your ideas, for your challenges, for making the world a better place. When I read them, I feel very humbled and confident that the world is in good shape. So keep thinking about science and technology, and I will see you soon.